Let's say you've got a sequence of vectors v1 up to vn belonging to r to the m or c to the m. The span of those vectors is a subspace of r to the m or c to the m. So you might want to know, how can I find a basis for that span? Or how can I find the dimension of that span? That's what we're going to do in this video. So here's the statement of the problem. You are given some vectors v1 up to vn belonging to r to the m or c to the m, and your task is to find a basis for the span of those vectors. Of course, once you've found a basis, you can then find the dimension, because the dimension is simply the size of the basis. The method we're going to use is as follows. In step 1, you write the vectors as rows, putting them as the rows of a matrix A. In step 2, you do row operations to A until you reach a row-reduced echelon form matrix. And finally, in step 3, the non-zero rows of this row-reduced echelon form matrix, turned back into column vectors, I claim are a basis for the span of v1 up to vn. So let me just show what's going on here. If your vectors were v1 is 1, 2, 3, and v2 is 4, 5, 6, then the matrix A you form out of those would have as its first row 1, 2, 3, and its second row 4, 5, 6. And you then do row operations to A to reach a row-reduced echelon form matrix, and then you take the non-zero rows and transpose them back into column vectors. We'll do a full example of this procedure at the end of the video. But before I go on to justifying why this method works, let's just comment about what's going on here. It seems a bit strange to turn our column vectors into row vectors and then do something and then turn them back into column vectors. The reason to do this is because we've already defined row operations and row-reduced echelon form, so we might as well use that. If we wanted, we could define column operations and column-reduced echelon form, and we could just do the column-reduced echelon form procedure to our column vectors. But since we've not done that, it's probably easier to work with row operations and row-reduced echelon form matrices, because we're already familiar with those. So here's a definition, in fact 2 definitions. If A is a matrix, the row space of A is the span of the rows of A, and the column space of A is the span of the columns of A. What we're going to show is that if R is a row operation, then A and R of A have the same row space. In other words, doing row operations to a matrix doesn't change its row space. So here's a statement of a lemma which helps make that precise. If you have any elements R1 up to Rn of a vector space V, and if you have 2 scalars A and B where A is not 0, and if you have 2 numbers I and j which are not equal and which are between 1 and n, then the following 3 things hold. First of all, the span of R1 up to Rn is the same as the span of R1 up to Ri minus 1, then A times Ri, then Ri plus 1 up to Rn. Secondly, the span of R1 up to Rn is the same as the span of the vectors R1 up to Rn in any other order. And finally, the span of R1 up to Rn is the same as the span of R1 up to Ri minus 1, and then Ri plus B times Rj, and then Ri plus 1 up to Rn. Before I talk about the proofs of those, let's just think about the connection between this result and row operations. If R1 up to Rn were the rows of a matrix A, then these vectors are the rows of A, so their span is the row space of A. What we have on the left-hand side of each of these equalities is the row space of A. But these vectors will be the rows of the matrix obtained by doing the row operation which multiplies row I by A to the matrix capital A. So part 1 implies that if you do the row operation which multiplies row I by the scalar lowercase a, then capital A and R of capital A have the same row space. Similarly, if R was the row operation which swaps 2 rows, then the rows of R of A are the same as the rows of A in a different order. So part 2 would say that doing that kind of row operation doesn't change the row space either. And finally, if R is the other type of row operation, which adds B times row j to row I, and if A is a matrix with rows R1 up to Rn, then these vectors here are the rows of R of A. So part 3 implies that this final type of row operation doesn't change the row space either. I think part 2 of this lemma is quite clear, because in any vector space, vector addition is commutative and associative. So if you have a sum of any number of vectors, you can reorder that sum in any way you like without changing its value. And that tells you that the span of R1 up to Rn doesn't depend on the order of the Ri's, because the two spans will have exactly the same elements. Part 3 of this lemma is going to be an exercise on your coursework 3. So the only part which I'm going to prove here is the part 1. So if we want to prove part 1, we're claiming that two sets are equal. So we should do it by a double containment argument. We should show the left-hand side is contained in the right-hand side, and the right-hand side is contained in the left-hand side. So let's take an element of the left-hand side, that is, an element of the span of R1 up to Rn. Such an element looks like a scalar times R1 plus a scalar times R2, all the way up to a scalar times Rn. So what it looks like is this. But we can rewrite this. Because the scalar A is non-zero, we could rewrite it like this. So the only thing we've changed is the coefficient of Ri. And in fact, we haven't changed it at all. We've simply rewritten it in a different way. But what you have on the right-hand side is visibly a linear combination of R1 up to Ri minus 1, and then A times Ri, and then Rn. So it's an element of the right-hand side, the span of R1 up to Ri minus 1, and then A times Ri, and then An, and then Rn. So we've shown that the left-hand side is contained in the right-hand side. For the other containment, let's take an element of the span of R1 up to Ri minus 1, and then A times Ri, and then Ri plus 1 up to Rn. What that looks like is some scalar times R1, plus some scalar times R2, and so on, and then some scalar times Ari, and so on, and then some scalar times Rn. But again, that's equal to A1 times R1, and so on, and then just rebracketing, it's Ai times A times Ri, and then up to An Rn. And this thing is visibly a linear combination of R1 up to Rn, because it's something times R1 plus something times R2, in the middle somewhere something times Ri, and finally something times Rn. As a linear combination of R1 up to Rn, it's an element of the left-hand side, which was the span of R1 up to Rn. So we've proved our lemma. So as a direct corollary, as I described earlier, it follows that if A is a matrix and R is a row operation, then the row space of A and the row space of R of A are equal. So because doing a single row operation doesn't change the row space, doing any sequence of row operations doesn't change the row space. So if A is a matrix and R is a row-reduced echelon form matrix, which you can get by doing row operations to A, then A and R have the same row space. Finally, we're going to show that the non-zero rows in a row-reduced echelon form matrix are linearly independent. So let's do that by introducing some notation for the rows, the non-zero rows of our row-reduced echelon form matrix. We'll call the non-zero rows R1 up to Rk. And we're going to suppose that the leading one in row I is in column Ci. So because of the row-reduced echelon form condition, C1 must be less than C2, that must be less than C3, and so on. So just so you can see what's going on here, I'll write down an example. Let's say our row-reduced echelon form matrix was capital R, and it was equal to this. Let's say 1, 0, 0, 2, 0, 0, 1, 3, 0, 0, 0, 0. Then in that case, K would be equal to 2, because there are two non-zero rows. C1 will be the column of the leading entry in column 1, in row 1, sorry. So C1 is here, and that's equal to 1. C2 will be the column of the leading one in row 2. So C2 will be equal to 3. Now let's suppose that a linear combination of these non-zero rows is equal to the 0 vector. We'll call that linear combination the sum from I equals 1 to k of ai times ri. Now let's consider, for a fixed j between 1 and k, the entry in column Cj of this sum on the left-hand side of that equality. Every ri except rj must be 0 in column Cj. That's part of the definition of row-reduced echelon form. So the only thing in that entry of the sum is aj times 1, which is aj. But since the whole sum is equal to the 0 vector, it then must be aj is equal to 0. This works for any j between 1 and k, therefore the coefficient of every one of these rows is 0, therefore the rows are linearly independent. So again, it helps to look at what happens in an example to understand what was going on in that proof. So let's look at what would happen in this example, where here was row 1 and here was row 2. Then if we had a1 times r1 plus a2 times r2, well, what that's equal to is a1, 0, a2, 2a1 plus 3a2. And I'm going to label the columns here. Here's column C1 and here's column C2. As I said in the proof, you can see that in entry C1 we just get a1. So if this thing is equal to the 0 vector, then a1 must be 0. Next, if you look at entry C2 of this linear combination, again, as I said in the proof, you can only get a2. And because the whole thing is equal to the 0 vector, a2 is also 0. That immediately establishes the linear independence of R1 up to Rk. Therefore, the non-zero rows in a row-reduced echelon form matrix are linearly independent. And that completes the proof that our method works. So let's now try an example of applying this method with some familiar vectors v1, v2 and v3. So these vectors at the top here. The next step in the procedure was to form a matrix whose rows were the transposes of v1, v2 and v3. So the first row of A comes from v1, the second row of A comes from v2, and the third row of A comes from v3. The next step in the procedure was to do row operations to this matrix A until you reach a row-reduced echelon form matrix. In this case, if you try doing row operations to A until you get a row-reduced echelon form matrix, the matrix you'll reach is this one. The final step in the procedure is to take the non-zero rows in that matrix, turn them back into column vectors, and then they are a basis for the span of v1, v2 and v3. Here we have two non-zero rows, and when we turn them back into column vectors, the first one turns into the column vector 1, 0, minus 1, and the second one turns into the column vector 0, 1, 2. It follows from our procedure that this is a basis for the span of v1 and v2 and v3.